All right, so in the last video, I walked you guys through two hypothesis tests for testing the mean and the standard deviation. In this one, I am going to say in chapter 8 again and do one now with a proportion. So like I mentioned in the last video, the process is the same, but the formula will differ. And I figure why not make another one anyway. So I'm looking at number 7 on page 458. So the premise of this problem is that there's a magazine article that reports that 11% of people buy takeout food every day. So a restaurant does a survey and they find out that 32 out of 200 of their respondents said that they take takeout food every day. And so what we're going to do is we're going to test that claim of the 11% being right or not. So since this is a proportion, we'll set up our hypothesis using P, right, for the proportion. And they're claiming it is 11%. So we'll have the null hypothesis to be that the proportion is 0.11 and that the alternative hypothesis is that it's not 0.11, because we're not trying to see if it's greater than or less than 11%. We're just trying to see, is it 11% or is it not 11%? And so we had 32 people out of 200 say that they did purchase takeout every day. So my X is 32 and my N is 200. All right, I have 32 successes out of 200. So my P hat, my sample proportion, is 32 out of 200, or 0.16. So already I can see 0.16, obviously not exactly 11%, but maybe it'll be close enough or maybe it won't. So our test will tell us that. So since this is a test for proportions, proportions always use Z. The alpha that we were given in the problem is 0.05, and looking back at our alternative hypothesis, it's not equal to. So we've got a two-tailed test. And so if I take out my formula sheet, I want to find my Z-score, but remember, like we said in class, the Z-scores are actually on the bottom of the t-distribution sheet. So if I have an alpha of 0.05 and I have to put it into two tails, I'm looking at that middle column there, and if I go all the way down to get the Z-score, it's 1.96. So I have positive 1.96 and negative 1.96 as my critical values. And so now I need to calculate my test statistic. If you look back at your Chapter 8 note sheet, the formula for the Z-test for proportions is you take P hat minus P and divide it by the square root of PQ divided by N. And so if I plug in, my P hat for my sample was 0.16. P from the population is assumed to be the 11%, so 0.11. And then in the denominator, it again uses P from the proposed population, so again 11. Q is always the complement to P, so 1 minus 0.11 would give us 0.89 for Q. So I'll plug that in for Q, and N was 200 people. And so when I run that through my calculator, I end up getting that Z is equal to 2.25. And so, actually, looking back at this question, there were two parts to it. One had you test it with an alpha of 0.05. So with a test statistic of 2.25, our conclusion will be that we reject the null hypothesis, which would then support the alternative. And so we'd have to say that the proportion is not 11%. But they actually ask you in that question as well, too, what would happen if the alpha was 0.02? Well, now if my alpha is 0.02, right, that's actually less. That should push my critical values out a little bit more. And in fact, when I look that up on my chart, now if I'm looking at the column that has 0.02 in two tails, and I look down on the bottom for my Z-score, I've got 2.326. Now everything else would have stayed the same in the problem, just that those critical values would have changed because our alpha changed. So our test statistic would still be the 2.25, but now that's going to fall in that fail to reject region. So we fail to reject the null hypothesis, and now our conclusion would be is that we can't say the proportion is not 11%. So you can see here a good little abuse of statistics, right? Depending on whatever you choose for your alpha, you could actually get two different decisions out of it.